Start?
Yes, please. This is the second lecture of Professor Friedrich Wagemann.
Okay, so today I will talk about the cohomology of Lie algebras. And as I said yesterday, it's the cohomology of Leibniz algebras has many very similar features. So I will discuss the cohomology of Leibniz algebras a little bit later in relation to what I'm going to say about Lie algebras. So let G be a Lie algebra. V a G module. Yeah, we talked about what a G module is yesterday. Oh, I see that. Yeah, you can see only up to here. So G algebra. Yeah, then one associates to G and V a space of cochains. And this space of cochains is by definition either the P times multilinear alternating maps from G to V, or and so the alternating P multilinear maps from G to V are the same as the K linear maps from the P's exterior product of G with values in V. Yeah, so alternating P multilinear maps from G to V, and here it's homomorphic linear maps from the P exterior product G. Yeah. So these are the Chevalley-Eilenberg P cochains. Yeah, and then there is the Chevalley-Eilenberg complex. Yeah, with these cochains and co-boundary operator, and then the cohomology, the Chevalley-Eilenberg cohomology, will be kernel of D from CP to CP plus 1 divided by the image of D from CP minus 1 to CP. Yeah, oh, this is kind of chopped off. Okay. Yeah, and the fact that D squared is 0 means that the image is a subspace of the kernel. Yeah, and so this quotient makes sense. So what I did not write for you on the blackboard yet is the co-boundary operator. So take C, P cochain, and D, C is a P plus 1 cochain, which is by definition C applied to the bracket, where I take two elements, xi and xj, from the list of elements from x1 to xp plus 1. I take them out. I put in their bracket, and so there's one element less here, and so it makes sense to evaluate C on these P elements. Yeah? And so it comes with a sign, -1 to the I plus j, and the sum is over all 1 I j. And then you have a second term. So this is the term where only the bracket is involved. And then there's a second term where the action of G on V comes into play. And so this term is xi acts on C of x1. I is taken out from the list. One, two, yeah. And so what is important here is that the signs are in such a way that when you put here x1, x2, yeah, and so on, and here x1, yeah, then the sign must be a relative negative sign. Yeah, so there must, yeah, okay, this is the sign rule. Yeah, and so the lemma is D composed with D is 0. Yeah, when this makes sense. Yeah, I mean here this D is going from CP to CP plus 1, and then this D here goes from CP plus 1 to CP plus 2. Yeah. Okay. Yeah, there are two, or there are at least 3 methods to prove this. The first one is brute force computation. The second one uses the simplicial identities. Yeah, so maybe you are familiar with this concept. Every time when you have a simplicial vector space, yeah, with phase operations di, then you can do the alternating sum of the di, and this gives you d co-boundary operator, which satisfies d squared equal to 0. Yeah, and this you can do here, but this is not the way I want to show it. I think the most instructive way to show d squared equal to 0 is to use the Cartan calculus, yeah, Cartan calculus, which you know perhaps from differential forms on a manifold, yeah. So Cartan calculus. Yeah. Note the similarity to differential forms on the Lie group with the algebra G. Yeah. Yeah. And so in order to, so this is here only a similarity, but in order to make this rigorous, these differential forms should be left invariant. Differential forms with values in V, in the vector space V. And so for differential forms, but also here for these P Chevalley-Eilenberg cochains, you have a Lie derivative operator, Lx, which goes from Cp of G to Cp of Gv, and which sends C to the map, which sends x1 to xp to, yeah, either you act on it or, yeah, either you act on it on the outside. Yeah, so X is in G also. Or you act on the inside. Yeah, in the highest spot. So this is the Lie derivative, and you also have an insertion operator, which sends you P cochains to P minus 1 cochains. Yeah, so this I call Lie derivative. And the insertion operator sends C to the map, which associates to x1, xp minus 1, C of x, x1, and this is a comma here, xp minus 1, insertion. Yeah. Okay, maybe, yeah, no questions. And these satisfy the Cartan relations, like for differential forms. And so, first of all, Lx is Ix composed with D plus D composed with Ix. Then Lx composed with Ly minus Ly composed with Lx is Lxy. Lx composed with Iy is minus Iy composed with Lx is equal to I of xy. And then the last one is that Lx commutes with D. Yeah. So these Cartan relations are probably well known for these Lie derivative and insertion operator on differential forms. And here in Lie algebra cohomology, they are proved exactly in the same way. Yeah. So there's even a book by Wagemann and Sternberg, which bases all equivariant cohomology calculi on these properties. Yeah. So let me not too much discuss these properties. Yeah, in some sense, when you try to prove them, for example, the D is very easily to derive from the A. Yeah, but A, you have to prove it. Yeah. So this is still a computation. Yeah. But here in these lectures, I will take these relations for granted, and I will not prove them. For example, for the case of Leibniz algebras, the same relations are true, and they are shown in the framework of left Leibniz algebras in the thesis of my student Simon Covès, yeah, which is available on the internet. So you can get them from there. So proof of d squared equal to 0 by induction. For p equal to 0, this is kind of clear. Yeah, what is a zero cochain? The zero cochains are just the elements of V. So take a zero cochain, let's say small v, and what is d squared of v? D squared of v is the 2 cochain. Yeah, so I can evaluate it on 2 elements, and this is dv evaluated on now x1, x2 minus x1 acting on dv of x2 plus x2 acting on dv of 1. And what is, so this is the second coboundary operator. And so what is the first coboundary operator? The D0 from C0 to C1 sends an element V to the 1 cochain, which one obtains just by acting on this element. Yeah. So this dV here means just act on the element. Minus x1 acting on x2. Acting on V plus x2 acting on x1 V. Yeah. And here you see this is exactly the property of being G module, which makes this to be 0. Yeah, so this is the case P equal to 0. And now P greater 0. For P greater to 0, we want to compute for C in C of G V. D2 of C evaluated on x1 to x p plus 2. Yeah. So the idea of proof is to write this as the composition of d squared c of the insertion operator insertion operator with d squared of c, yeah, and then evaluated on x2 to xp plus 2, and then move the insertion operator through these 2 d's, yeah, with the help of these identities. Yeah? So this is what we are going to do, because the first, yeah, when you take together I x1 with the first d here, we can write it by the property A, yeah, which you still see, as Lx1 minus d composed with Ix1 composed with dc of x2 yeah, composed with D of C equals to XP plus 2. And now you have Lx1 composed with D minus D1 D of C of x2 plus 2. And so yeah, I have now once again this situation where I have Ix1 composed with D, Lx1 composed with D minus D, and here once again by property A I will, oh, this you don't see anymore. Then I go to the other board. Yeah, so here once again by property A, I will write this as Lx1 minus, yeah, there's a D in front, Lx1 minus D composed with 1. Oh, and this, all this is applied to C, which is then applied to x2. And what did we gain from here? We gain now that we have now d squared again here. On a lower degree cochain. Yeah, this is d squared again, but on a lower degree cochain. So this gives 0 by induction hypothesis. So this term is 0, and here we have also 0 by property. By which property? By property. Yeah, and so this shows that d squared is equal to 0. Okay, you see that with the Cartan identities, this works very automatically. Yeah, and I will not show you that d squared is 0 also for the co-boundary operator in Leibniz cohomology, because there the computation is exactly the same. Yeah? Because the Cartan identities are still valid. Okay, now we come to interpretations. Interpretations of low degree homology spaces. So I told you already the D from C0 from GV to C1 of GV is just the map which sends V to the map which sends X to X acting on V. Yeah? And so H0 of G is kernel of this D divided by the 0 map. Yeah, because Yeah, the space C-1 here is 0, and there's no differential coming into C0, so the image here is 0. So this is just the kernel of this map. Yeah, and so what are the elements which are sent to 0 under this map? These are the elements V of V such that x dot V is 0. Yeah, and these are called the invariants. This is denoted like this, space of invariants. Okay. And you can have some easy examples of invariants just by taking your favorite D algebra and your favorite G module and see what it gives. Usually this is fairly easy to compute if your module is not too complicated. So I have some examples here. So GLN K x on K to the N. And what are the invariants? K to the N, GLN K 0. Yeah. No element is invariant. This even works with SLN or SL3 acting on R3. Yeah, no invariance. In order to have some invariance, one needs either the trivial module, V A trivial module. So any VG is just V A. All elements are trivial. All elements are invariant. Either this or another way to have invariance is to take solvable or nilpotent Lie algebras. So when you take G equal to N3 of R, the matrices of the form 0, something, 0, 0, 3 by 3 matrices with values in R. This is the nilpotent Lie algebra and acts on R3. And here the invariants are very clear. It is the vector space generated by 1, 0, 0. All these elements are invariant under the Lie algebra action. Okay, now this is maybe you know. Okay, then let me come to P equal to 1. So we have D from C1 of G, B going to C2 of G, B. And what this is just a hom of G, V, and sends a map F to the map, to the map DF. And DF is a two-code chain, which is F of the bracket minus x1 acting on F2 plus x2 acting on F. And so this is Yeah, and so the co-cycles, this is the kernel of B, yeah, are here just the F on G V such that this identity is true. F of x1 minus x2 plus x2 acting on 0. So this we probably don't see anymore. Yeah, this we don't see. Yeah, so meaning this identity, this equal to 0. And what does this mean? Yeah, so this is kind of a derivation property. Yeah, write it like this: f of the bracket is x1 acting on x2 minus x2 f of. Yeah, so this is a derivation property. Yeah, and so in a V derivation, yeah, maybe you ask yourself why there's a minus sign here. Yeah, this comes from this exchange of x1 and x2. Yeah. So the inner derivations are the CV of x, which are just x on V. And we already saw for some V, and this is B1 of G, these the co-boundaries. The one co-boundaries. And so the cohomology is Z1 of GB divided by B1 of GB. So it is V derivations modulo inner V derivations. So this is still kind of abstract, but for example, for V equal to K, yeah, what does this give for the trivial module? These actions here are trivial, so this is 0 and this is 0. So this is just the maps from G to V, yeah, from G to K. So the maps in the dual of G, which vanish on the bracket. Yeah, so H1 of G is just G, the F G star, dual of G, such that F of 0 for all x1 G. So this is just G over G, G. Yeah. And so this measures how much G is far from its commutator subalgebra GG. Yeah, and so to have an example here, for example, H1 of GL and K is K because GL and K is SLA already seen in Karel de Kimp's talk that GLNK is the sum of K and SLNK. Yeah. And yeah, what I also wanted to say is what I also wanted to say is, first of all, are there questions in the chat? No. So what I wanted to say is cohomology of Lie algebras already appeared in other lectures. Yeah. So for example, Said Benayadi was talking about the symplectic structure on a Lie algebra. Yeah. And this came down to a co-cycle, a two co-cycle with trivial values. And okay, Abdenasser Makhlouf did not talk about Lie algebra cohomology, but about Hochschild cohomology, and there are very similar mechanisms in at stake. So what I want to say very briefly is homomorphisms of Lie algebras induce homomorphisms in cohomology. Yeah. And short, yeah, in the other direction. Yeah. Short exact sequences of G modules induce long exact sequences in cohomology. Yeah, these are features which are true for most cohomology theories, so they are very, very general. So let me just comment on one interpretation which will become important later on in infinitesimal deformation of the Lie algebra G is a Lie algebra structure on G of t, the A0 plus A1 t plus A2 squared polynomial with aig, yeah, up to order 1. Order in T. Yeah. And two such are called equivalent. If there is a morphism of the algebras phi in G of t such that such that we have a commutative diagram of this form. Yeah, here we have this is the evaluation at t equal to 0. Yeah, t equal to 0, and this must commute. So this implies, in fact, that phi 0 is the identity. Yeah. And So infinitesimal deformations of a Lie algebra up to equivalence are classified by H2 of G with values in the adjoint representation. Yeah, this is kind of what you already talked about in Professor Machlouf's lectures. So this is a theorem, is in bijection with infinitesimal deformations to equivalence. And so in order to show this, actually, when you write down the hints on the proof, A of t is A plus t, A1 plus O of square. Yeah, and now if you write A of t, B of t, C of t is equal to plus B of t, C of t, C of t. And you the bracket A of t, B of t is some should start with AB, yeah, plus t times omega of AB. Yeah. So when you write down the Jacobi identity, which should be true up to order 1 in T, yeah, then you get the co-cycle identity for omega, yeah, because you have here either the terms, yeah, you can choose only one term in T here of these three. Yeah? Only one can be in T. Yeah? Otherwise, it goes into O of T squared. Yeah, and so either you take the omega term here, or you take the omega term here. If you take the omega term here, then you get the action A dot, yeah, A dot omega B C plus cyclic, and or you get you take the omega term here, then you have to take the bracket here, omega of A bracket of B C plus cyclic, and then this is one way to express the co-cycle identity. Yeah, and equivalences give co-boundaries. Yeah. And equivalences give co-homologous deformation. So, and I have to say one thing more about this. Note that Professor Machlouf said something much more general than this. Yeah, in Nasser's lecture, there was not only H2 governing infinitesimal deformations up to equivalence, but actually the first non-zero term other than zeros term in deformation gives two co-cycle see lectures. So if H2 of G, yeah, and this is with values in the adjoint action is 0, then any deformation of, let's say, formal or polynomial is equivalent to the trivial. Yeah, and so this is something which is very important in the classification of Lie algebras. Yeah, when you this is exactly similar for Leibniz algebras, and so it comes also in the classification of Leibniz algebras. You take a dimension, let's say dimension 5, and you want to classify all Leibniz algebras of dimension 5, then it is very important to know these cohomology spaces, because they tell you in which directions you can deform your Lie or Leibniz algebra non-trivially. So this is what I meant when I said cohomology is a tool, yeah, which is important in the structure theory of these algebras. Okay, let me take the last 10 minutes to skip the link between extensions and H2. Yeah, actually, if our general module V, yeah, the H2 of G with values in V classifies abelian extensions of G by V. Yeah, this is done in detail in the lecture notes. I will not have the time to talk about this. Actually, there's also an interpretation of H3. Yeah, H3 is related to crossed modules. And this we will not do either, but see my book. Actually, I wrote a book on crossed modules of groups of Lie algebras and associative algebras. It is on my web page, so you can just have a look on this interpretation of H3 in terms of crossed models. Yeah, I have to speed a little bit up. Report on the cohomology of semi-simple algebras. Yeah. So in order to put into perspective our theorem with Jörg Feldfuss, I want to talk to you about what is known about the cohomology of semi-simple Lie algebras in order to compare it later to the cohomology of semi-simple Leibniz algebras. So K is a characteristic zero field, and G a finite dimensional Lie algebra. And we have already seen in Karl de Kimpe's lectures what it means to be semi-simple. Actually, there are many equivalent formulations of this. One of them is that G is a direct sum of simple Lie algebras, or another one is that the killing form is non-degenerate, or another one is that G does not have any non-zero abelian ideals. G does, and still another one is that G does not have any non-zero solvable ideals. And still another one is that the radical, yeah, exactly the same radical as Karl de Kimpe talked about before, the radical is 0 for semi-simple Lie algebra. This is also written in my notes. So what I want to highlight here is On the one hand, there's a theorem of Samuelson, Chevalley-Eilenberg. I call it like this because it was first formulated by Hopf in 1941 and Samuelson in 1941, and then proved in a very comprehensible way by Chevalley-Eilenberg in 1948. So for G semisimple, homology with trivial values is graded Hopf algebra with generators in odd degrees. Yeah. And actually, meaning here, this is in fact an exterior algebra. Yeah, because by Miller-Moos theorem, the graded Hopf algebra is always a tensor product of an exterior algebra and polynomial algebra. And as the Lie algebra is finite dimensional, there can be no polynomial part of it, so it must be an exterior algebra and odd generators. And so let me finish with Whitehead's theorems. So first the theorem, G semisimple, M G module, finite dimensional G module, and with trivial invariance, then all cohomology vanishes. Yeah, and maybe better known are first and second Whitehead lemma. So first lemma is that yeah, now M is just finite dimensional. H1 of G M is 0. Yeah, did I say semisimple? G semisimple. And second Whitehead lemma, G semisimple and finite dimensional. H2 of G and M is 0. Yeah, and so let me not get into proofs here. This is just to tell you what is known about the cohomology of semisimple Lie algebras. Maybe yeah, this is Samuelson. And so why is this important? Yeah, that actually H1 is very much related to extensions of G modules. Yeah, in every extension of G modules, you have yeah, when you have an extension of G modules, N M prime M 0 or E. Yeah, and this extension of G modules is governed by the homomorphism in the homomorphism from M to N. Yeah, and actually this gives a cocycle, yeah, a one cocycle of G with values in the homomorphism from M to N. And so the fact that H1 is 0 tells you that all homomorphisms, all extensions of modules split. And this is Weil's theorem, yeah, that all extensions of modules for a semisimple Lie algebra of finite dimensional modules for semisimple Lie algebra split. Yeah, so this is a very important structure theorem, and this is also a very important structure theorem. We saw in Karel de Kimpe's lecture at the end that Lie algebra always, finite dimensional Lie algebra always have Levy decomposition, yeah, into the radical, into a semi-direct product of the radical and a semi-simple subalgebra. Yeah, and this H2 being equal to 0 tells you that the usual extension of G by the radical on the one hand and with quotient semi-simple Lie algebra must split. Yeah, and so this theorem here implies the existence of the Levy decomposition. So these are very important structure theorems, and I will stop here. You have maybe questions?
I have a question, please.
Thank you, Friedrich.
Yes. I have a question, please.
Yes, go ahead.
Please.
Okay, so at the very beginning, why Chevalley and Eilenberg defined the map D as this? How did they get this expression of D?
Yeah, they explain that it comes from differential forms. Yeah, so this is the expression of this is one expression of the de Rham differential on differential form. Yeah. Differential on differential forms. Yeah, one expression is exactly in this sense. Yeah, although I said when you take usual differential forms, they have trivial values. Yeah, so you don't have the action term in there. But if you have differential forms with values in module for the Lie algebra of vector fields, yeah, then you have even the module term in it. Yeah. So it comes from differential geometry.
Okay, thank you. So last one, please. So at the interpretation of the H2, you said deforming a Lie algebra. What do you mean exactly by deforming a Lie algebra?
Exactly like in Abdenasser Makhlouf's lectures. Yeah, so take formal deformations. Yeah, this was the easiest framework for deformations in his lecture. So you mean so you take a formal series with values in the Lie algebra. Yeah, so all the you have T, yeah, powers of T, and the coefficients of these powers of T are elements of the Lie algebra, and you talk about if you have a structure of a Lie algebra on these formal series with coefficients in the Lie algebra, then you talk about a formal deformation of this Lie algebra. And
Thank you very much.
You suppose that on the zeros term, it's the usual, it's the bracket the Lie algebra came with. Yeah.
Okay.
I see there. You're welcome. I see there's a question in the chat also. Does the converse of Whitehead's lemmas hold? This is a very interesting question. I don't know for the first Whitehead lemma, and I know that Pasha Susmanovic worked on the converse for the second Whitehead lemma. Yeah, so it is on the archive. Look up Pasha Susmanovic. I will write this down. Yeah, so he has a paper on the converse of the second Whitehead lemma, and maybe I don't remember in detail, but maybe he also discusses the converse of the first Whitehead lemma in this paper. So please look there.
Thank you. There is another question from Madagascar. Please, you may ask.
Go ahead.
My question is not about the cohomology, but yesterday you talk about Leibniz algebra. So can we study a representation of Leibniz algebra?
Yes, yes. Actually, what we saw today is only the introduction to the cohomology of Leibniz algebras with values in a bimodule. Yeah, and this is what we are going to talk about tomorrow. Yeah, so this will come.
Okay, thank you.
Tomorrow.
Thank you. Other question? Ah, yes.
Thank you. Thank you. So I have another question.
Yes.
You told about the interpretation of H0, H1, H2, and H3.
Yes.
So is still an open question, the interpretation of H4 and so on?
This is also a very good question. Yes, actually, what is known is that the Hn, yeah, you can have Hn of GV is unida products of crossed modules with long exact sequences of G models. So I don't have the time to explain this in detail, but you can express every Hn, yeah, in terms of unida products of lower dimensional cohomology with which you splice together with an exact sequence of G modules. So this gives one kind of interpretation. Yeah, this is the best I know of. This is Gerstenhaber. I think it was 1964. Maybe 466. Yeah, this is the best I know of.
Okay, thank you.
You're welcome.
Thank you for the question. Any other question? No. Well, let's thank Friedrich again.
Thank you.